Now, the next concept I want to talk about is something called Boyles Law, and what Boyles Law says is the pressure and the volume are going to be inversely proportional, or maybe another better way of saying that is if you take the pressure and you multiply it by the volume, then that's just going to essentially be a constant number. So if we were to take the pressure inside of a cylinder right here, and we were to multiply it by the volume, it has to be some constant. And not surprisingly, if I were to compress this cylinder, volume goes down, then go ahead and make the volume go down, then the pressure has to correspondingly go up, and these two numbers have to multiply out to whatever they were before. So if right here, say the pressure was 1 and the volume was 10, then 1 times 10 is equal to 10. Now right over here, maybe the volume is equal to 1, and so pressure times volume has got to be equal to 10. If the volume is equal to 1, that tells you that the pressure has got to be equal to 10. So I'm probably not telling you anything that you don't already know. If you squeeze a 2-liter bottle of Coke, then there's more pressure in there. So if you were to, say, double the pressure of something, then the volume has to be halved. So kind of once again, what Boyles Law says is if you multiply the pressure by the volume, then it's got to be a constant, and we can have scenarios where there's a large pressure and a small volume. If we went ahead and we expanded an object, made the volume a little bit larger, then the pressure is going to be a little bit smaller. Now, applications of Boyles Law is going to be scuba diving. If you think about it, if you're way down here, then the pressure is going to be relatively large, and as you go up, well, we know the pressure is going to go down. Now, if you're scuba diving and you have your lungs, what you're told to do is you're told to exhale as you go up. If you were to hold your breath, then what would happen is as this pressure goes down, then the volume is going to go up. And so if you held your breath, your lungs would expand, and at some point they would burst. So very, very, very important is going to be Boyles Law. Pressure times the volume is going to be a constant. So what you're told to do is you're told to exhale, and that way your lungs can stay the same size. So a nice example of this is here I have a balloon, and it's at atmospheric pressure and it has some volume. And I'm putting it into a vacuum chamber where I'm going to decrease the pressure. Decrease the pressure means I am correspondingly increasing the volume of this balloon. So bigger, 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 bigger. Now I'm going to go ahead and turn the vacuum pump off and unhook it. So now I'm increasing the pressure and decreasing the volume. Now, marshmallows are a little bit different than balloons, so here I'm going to take a marshmallow and put it on there. I'm going to pull a vacuum on it, and you're going to see the same thing as the balloon. Decreasing the pressure is going to lead to an increase in the size of the marshmallow. So you can kind of see it growing, growing, growing. One difference between the marshmallow and the balloon, however, is air can't really pass through the skin of the balloon. Air can be sucked out of the marshmallow, so now when I decrease the pressure, I've sucked all the air out of the marshmallow, and I have a sad, desiccated little marshmallow that kind of looks like your brain after a physics test. It is, however, still very tasty. Just kind of a gut check on this is suppose you have an airtight piston, and the volume is increased by a factor of 3. What would happen to the pressure? The pressure should go down to 1/3 of the original pressure. Now, I did mention this briefly in the last chapter, but I'll mention it again. We can have a buoyant force in the fluid called air. So Archimedes' principle is going to apply to air or gases as well as liquids, and it really pretty much states the same thing that it did in water. If you have an object, and it's an object like this, and you go ahead and you put that object into some air, then it's going to displace some air, and it's going to experience a buoyant force upwards equal to the weight of the air that is displaced. So, we're going to just have a buoyant force that's going to be equal to the weight, and in this case it's going to be the weight of air instead of the weight of water. So take, for example, a gas-filled hot air balloon. It's essentially going to experience a buoyant force, right? There's going to be less force here than there is right here. So there's going to be a net buoyant force, and that buoyant force is going to be in the upwards direction. And the balloon is going to rise and rise and rise and rise and rise up until the point where the weight of the displaced air is going to be equal to the weight of the balloon. Now, you may say to yourself, well, we have the weight of the atmosphere, and we've already seen that it's, a big, huge weight. How come the balloon doesn't just get crushed? Well, there's gas inside the balloon, and it just prevents the atmosphere from collapsing them. So, take for example, I'm going to make my gas inside the balloon right here green. And this is me launching a helium-filled radiosonde. And this gas right here is, kind of bouncing off the surface, and the pressure exerted there is going to be equal to or larger than the pressure due to the atmosphere. And again, as this balloon gets larger and larger, or as this balloon rises and rises and rises, it's going to get larger and larger and larger. And actually, by the time this thing hits the top of the atmosphere, it's going to be the size of a school bus. But what's going to happen is, as the balloon rises, it's going to expand. The atmosphere is going to get less dense, and at some point, it's going to either reach an equilibrium with the atmosphere, or the balloon's going to stretch such that the elastic pops. So let's just do another quick little calculation. We've done one where we talk about people floating on water. How come they don't float when they're on air? So remember that this buoyant force is going to be equal to the weight, and in this case it's going to be of the air displaced. And you could use the same argument that we did in the previous lecture to say this is going to be the density of air multiplied by the volume of the person multiplied by gravity. And the density of air is going to be 1.25 kilograms per cubic meter. Typical volume of a person is going to be 0.1, and gravity is going to be 10, and so this is going to be 1.25 newtons. And we could kind of convince ourselves that if we had a 75 kilogram person, then that's going to translate to 750 newtons. So yes, whenever you step on a scale, it's not reading your true weight. There's going to be some buoyant force in the upwards direction, but it's going to be relatively small compared to your weight, which is going to be, maybe 750 newtons. Now I kind of want to change gears and talk a little bit about what happens when fluids are in motion, kind of wrapping up the chapter. And it turns out there's going to be two types of motion that we can talk about. We can talk about laminar flow or turbulent flow. If you take a look at these two examples, A and B, if we were to take an air parcel, we could kind of put it at each one of these little locations right here. So kind of do that for all these guys. And in laminar flow, the fluid is going to flow in a smooth, continuous fashion. And we have these little streamlines right here, which essentially says that this piece of air is going to travel along this line right here. This one's going to travel along this line right here, and so on and so forth. And you can see that it looks relatively streamlined or smooth. If we have turbulent flow, then you can follow the streamline, and yeah, that looks smooth. But this one right here, it kind of breaks up and does something kind of funky. This one right over here kind of breaks up and does something kind of funky. And essentially this looks a lot like an eddy, and let me just tell you that turbulent flow is going to be very, very, very messy. It's going to be hard to deal with. Everything that we're going to talk about is going to be laminar flow, streamlined flow, or smooth flow, if you will. You can see kind of examples of this where here we kind of have the wing of an airplane, and we have these little streamlines, which are again going to be where an air parcel is going to kind of travel. And right over here it's going to be relatively smooth. Sure, it breaks up a little bit, but it doesn't look too awful bad. If this airplane wing was kind of tilted up like this, you can kind of see how these streamlines kind of break up into little tiny pieces, and again it's going to be relatively messy back here. Now, as long as we're talking about streamlined flow, then we can say some interesting things about fluids that are in motion. If we had a pipe, say a piece of 4-inch PVC right here, and it had some water flowing in it, and this water was flowing at a certain speed, so we'll kind of say that here we have some area and here we have some speed. It turns out that if the pipe goes down to a constriction, suppose it goes down to a piece of 2-inch PVC, then we can say something kind of interesting relating the velocity and the area over here. It turns out that if you take the area times the velocity from this big piece of PVC and you multiply them together, that's something called the volume flow rate, and that's going to be something that is going to be a conserved quantity as long as the density doesn't change. So this area times the velocity on the first side of the house has got to be equal to the area times the velocity on the second side of the house. And kind of like as you would expect is right over here we have the area going down, and this times this is some number. It's got to be a constant, so if the area goes down, the speed's going to go up. So if you stick your finger in front of a garden hose, for example, you're kind of closing down this area, and the water squirts out faster. So there's a good chance that we've all played with garden hoses and you know exactly what I'm talking about.